It appears as a bruise on the oldest light in the universe, a region of sky colder than it should be, colder than theory allows. No telescope was looking for it. No equation predicted it. And once it was seen, it refused to go away. This is the cold spot. The cosmic microwave background, known simply as the CMB, is not a picture of space. It's a picture of time. This radiation was released roughly 380,000 years after the Big Bang, when the universe cooled enough for light to finally move freely. Every direction we look, we see it. A near-perfect afterglow of creation itself. And it is almost perfectly uniform, almost. Tiny temperature variations, 1 part in 100,000, are expected. They're the seeds of galaxies, clusters, and the large-scale structure of everything we see today. These fluctuations are well described by standard cosmology. Measured, modeled, reproduced. Except one. In the southern sky, centered in the constellation Eridanus, lies a region far colder than anything surrounding it. Roughly 70 microKelvin below the average. Vast, smooth, anomalous. The cold spot. At first it looked like noise, a statistical fluke, the kind of thing that vanishes when instruments improve. It didn't. The first clear detection came in 2004 from NASA's Wilkinson Microwave Anisotropy Probe, WMAP. The mission was designed to map the CMB with unprecedented precision, and its data transformed cosmology. But buried in the maps was something unsettling. A cold region spanning about 5 degrees of sky, 10 times the diameter of the full moon. Its temperature depression was deeper and more coherent than simulations predicted. In standard lambda CDM cosmology, such a feature should be extraordinarily rare. Not impossible, but unlikely. The statistical significance hovered around 1 in several thousand. Enough to raise eyebrows, not enough to rewrite physics. So scientists did what they always do. They checked everything. Instrument error came first. Was it a detector artifact? A calibration issue? A scanning pattern glitch? WMAP's data was reprocessed, cross-checked across frequencies, compared between detectors. The cold spot remained. Foreground contamination was next. Maybe it wasn't cosmological at all. Perhaps something closer. Galactic dust, synchrotron radiation, unresolved radio sources. Those signals have known spectral fingerprints. The cold spot didn't match them. Then came Planck. Launched by the European Space Agency in 2009, Planck had higher resolution, broader frequency coverage, and tighter control of systematics than any CMB mission before it. If the cold spot was a mirage, Planck would erase it. In 2013, Planck released its maps. The cold spot was still there, sharper, clearer, undeniable. At that point, the question changed. Not is it real, but what is it? To understand why the cold spot matters, you need to understand the rules it seems to break. The standard model of cosmology assumes the universe is statistically isotropic and Gaussian on large scales. In plain terms, if you zoom out far enough, the universe should look roughly the same in every direction, with temperature fluctuations following predictable random patterns. The cold spot doesn't fit neatly into that picture. Its shape is too smooth. Its scale is too large. Its temperature deviation is too extreme. On its own, any one of those might be tolerated. Together, they push against the edge of statistical comfort. And so the investigations began. One of the earliest explanations was deceptively simple: a void. Specifically, a supervoid, an enormous region of space with far fewer galaxies than average. If CMB photons pass through such a void, they can lose energy via the integrated Sachs-Wolf effect. appearing colder when they reach us. This idea had appeal. It used known physics, no exotic assumptions, just large-scale structure doing what it does. Astronomers searched for evidence. Galaxy surveys did find an undersense region in the direction of the cold spot, a void stretching nearly 1 billion light-years across. But there was a problem. Even a void that large shouldn't be able to produce a temperature drop of that magnitude. Detailed simulations showed it could explain, at best, about 20 to 30% of the observed coldness. Helpful, but insufficient. The void explanation couldn't close the case. Others proposed a more subtle statistical origin. Perhaps the cold spot is simply a rare fluctuation, an unlucky draw from a cosmic lottery. After all, the universe is vast. If you look long enough, improbable things will happen somewhere. This argument hinges on how you define somewhere. The cold spot wasn't predicted beforehand. It was found after scanning the sky. That introduces a look elsewhere effect, weakening its statistical weight. When analyzed conservatively, the anomaly drops to around 2 to 3 sigma. Uncomfortable, but not catastrophic. Still, this explanation has a weakness. It doesn't explain why the cold spot has unusual non-Gaussian properties. Its temperature profile doesn't match the random fluctuations expected from inflationary models. It looks structured. Intentional is the wrong word, but atypical fits. Then came the more exotic ideas. Topological defects from the early universe. Cosmic textures. Wrinkles in space-time formed during symmetry-breaking phase transitions, moments after the Big Bang. These objects, predicted in some high-energy physics models, could imprint localized temperature anomalies on the CMB. One such texture passing through our line of sight could, in theory, produce something like the cold spot. The math works. The problem is evidence. If textures exist, they should leave other signatures, polarization patterns, additional anomalies. So far, those signatures remain elusive. Possible, but unconfirmed. And then there's the idea that makes physicists shift in their chairs. Eternal inflation. In some models, our universe is just one bubble in a vast multiverse, regions of space-time constantly inflating, spawning new universes with different physical properties. If another universe collided with ours early in cosmic history, it could leave a scar, a circular region of anomalous temperature, a cold spot. This hypothesis is speculative, but it isn't fantasy. It emerges naturally from certain inflationary frameworks. Researchers have searched the CMB for collision signatures, rings, disks, asymmetries. Some analyses suggest the cold spot is consistent with a collision profile. Others strongly disagree. No consensus, no confirmation. Just an unsettling possibility that we're seeing evidence of something beyond our universe. What makes the cold spot especially troubling is not any single explanation, but the fact that none of them fully work. Void? Too weak? Fluke? Too structured? Textures? No corroboration. Multiverse? No testable proof. Each theory explains part of the data. None explain all of it. And in physics, that's dangerous territory. Zoom out far enough, and the cold spot becomes part of a larger pattern. Other anomalies exist in the CMB. The quadrupole-octupole alignment, the hemispherical power asymmetry, parity violations at large scales. Individually, they're marginal. Together, they hint at something incomplete in our understanding of the early universe. Not wrong, incomplete. And the cold spot is the most visually obvious of them all. A reminder that even the most precise cosmological model ever built still has loose threads. What does this mean for physics? At minimum, it tells us the universe is messier than our clean equations suggest. At maximum, it hints that our assumptions about inflation, isotropy, or even the uniqueness of our universe may be flawed. Or it could mean nothing at all. A cosmic coincidence, a statistical bruise we happen to notice. Science is patient. It doesn't rush to conclusions. It waits for better data, sharper tools, clearer patterns. Future surveys, like the Simons Observatory and CMBS-4, will measure the microwave background with even greater sensitivity. Large-scale structure maps will refine our understanding of voids. Polarization data may confirm or rule out exotic origins. The cold spot may yet fade into normality, or it may become the first crack in a much larger theory. For now, it remains a cold region in ancient light, a deviation written into the fabric of the universe itself, not loud enough to overturn physics, too persistent to ignore. The universe whispered something unexpected, and we're still trying to understand what it meant. Documented, unresolved. This is Unreal Mind.